Shane, you want to go ahead and do an intro?
Sure. Okay. Welcome to our first CESG seminar for 2021. And we're glad to have Dr. Shaoshan Liu to give a presentation on a very trendy topic about autonomous vehicle. Okay. And Dr. Liu is a CEO of Percept In, an intelligent transportation company. And his technical researcher focuses on autonomous driving technologies and robotics. He has published over 17 research papers, over 40 US patents, and over 150 international patents. And he's a senior member of IEEE, a distinguished speaker of IEEE Computer Society, and a distinguished speaker of ACM, and founder of IEEE Special Technical Community on Autonomous Driving Technology. And he received an MPA from Harvard University and a PhD from UC Irvine. And one part not mentioned in this short bio is that actually Dr. Liu also co-authored books regarding autonomous vehicle. Okay, so let's welcome Dr. Liu, please.
Well, thank you so much for the introduction. Really honor to give a talk here. So today we're going to talk about designing computing systems for autonomous machines. That's really my main area of research. And then in this talk, we're going to explain why, what are the challenges, and what are the solutions that we have tried, and what are the solutions we have not yet tried that maybe we can explore together in the future. So at the beginning of my talk, I always ask the same question. It's quite fun to ask these kind of questions. We talk about processors for robots, pretty much autonomous machines or robots. So what do you think is the best selling robotic processor so far? Given the talk, it's not quite interactive as a face-to-face talk. So I'm just gonna wait for a few seconds and then you can think about answer. You don't have to answer me.
Yeah, if the students could use the raise hand function, then we can kind of go from there.
Yeah, if you're interested to give an answer, welcome to try. What do you think is the best? Or
anybody else, I guess.
Yeah, anybody else. What's the best selling robotic processor so far by volume, the number of units shipped? Take a wild guess. I think it's quite a fun question to ask since we are dealing with robotic processors.
Go ahead, Changji.
I'm just throwing a guess. I guess ISA wise, probably ARM and
ARM. It's not the processor. ARM. It's
yeah, ISA wise. I think
okay.
As to manufacture, I don't know. It's probably something like mobile. So I guess Qualcomm.
Very good guess.
I don't know.
Very good guess. Any other guess?
Doesn't NVIDIA have a line of ARM processors with GPU with reasonable GPUs on?
You would think.
Maybe not. Okay.
Well, let's move on then.
Okay. Well, let's see. Yeah.
Let's see. It's STM32. They sold 1 billion units. So basically no GPU, basic ARM controller. The reason being that they have 60 I/O pins. Most robotic processors, they are sensor rich, meaning that they deal with different sensors. So they go into robots, like the cleaning robots on your right side. So that it's a $5, $10 chip, very affordable. But then they have a very rich I/O interface, GPIO interface, so that if you deal with different kind of sensors, it's very easy to deal with those. So that's one. So next question, what's the most expensive robotic processor so far? Any other answer? It's not ARM, I can guarantee you that. So see if there's any answer from the audience.
The Intel Atom series, maybe?
Atom, no way. It's quite inexpensive. It's a few $100s. I don't think that's the most expensive robotic processor so far.
Xeon?
Xeon. Well, they're expensive, but not that expensive, right? I mean, any NVIDIA PX2, when they first came out, they sold it for like what, 20, 30,000 per unit. Xeon is like $1,000. So likewise, let's move on. It's not as interactive, but you can think about it. But here's the answer. It's RD 6000. Costs, say, $3 million per unit. It goes to space. It powers the Mars rover. When you look at the spec, it's crazy, right? It looks like a chip from the 80s or 90s. The reason being that it has to be radiation tolerant, such that when you ship it to space, the radiation does not hurt the chip. You can still power the robot. So what does that tell us? I mean, it's a very diverse requirements for robotic computing. The I/O requirement, workload requirement, scenario requirement, in this case, usage requirements. When you ship something to the Mars, of course, it costs that much, $3 million per chip. They have two versions, interestingly. They have FPGA version, which they actually ship, and there is an ASIC version. It's too expensive. I don't think they ever completed that. So it's quite interesting learning. So it's very diverse requirements for robotic processors. That's why it's very fun to delve into this field.
So who's the manufacturer of this chip?
Go ahead.
So who's the manufacturer of this chip?
It's Microsemi or Xilinx. I don't remember. One of them. Yeah.
Okay.
So what do we do at Perception, or what do I do for my own research? So understanding that there's a diverse requirement for robotic process, I really want to try to summarize or identify the common traits in robotic computing and see if we can design a architecture or computing system for these kind of workloads. So today's talk is about how we approach this problem, designing processors or computing systems in general for robotic or autonomous driving workloads, and what we have tried, what have failed, and what are we doing now. So that's the what we're going to talk about in this talk. So let's look at this picture, quite interesting picture as well. Different kind of mobile robots, ranging from like iRobot, kind of cleaning robot, to Mars rover. Then in between, you have a L4, a level 4 autonomous vehicle, just like the one from Google. In the middle, you see the Perception vehicle. That's the Micromobility vehicle. You go one step down, you see a mobile robot for exploration. Then you go one step down, you see the cleaning robot. So that's pretty much the spectrum. You can add the drones and other robots here, but that's pretty much the spectrum. Then you try to analyze the workloads in each one of them, and you see if there's any common workloads or common traits for these different kind of robots. Then we see here the figure on top of it, the architecture of it. You see the blue part, they are the sensors. You're dealing with a lot of different sensors. I'm just listing a few here: millimeter wave, radar, camera, LiDAR, GPS, IMU, a lot more. Then what happens is that from the left to the right, you go through different stages. Then each stage, you see additional constraints. Then at the end, you produce a control signal to actually control the robot. So from the left, we see if you have a camera, you get 2D perception. Quite interestingly, in recent years, a lot of deep learning techniques to help you to detect things, to identify or do segmentation. Then you have LiDAR, the 3D sensor. Then you deal with 3D perception. Meanwhile, LiDAR can go into localization to can generate the position results, localization results for the robot. Then next stage, you can kind of fuse the 2D information and 3D information, performing sensor fusion. And at that point, you can add radar. Then once that's done, you kind of understood your environment. You know what's around you. Then you do tracking. You want to keep track of the movement of different objects around you. Then once that's done, you say, I have tracked these objects. Then why don't I predict their movement so that when I make my own movement, I know how to deal with them. So you do prediction. Then once prediction done, you deal with planning, meaning that you have to generate a plan for yourself. Then at the end, you have control, meaning that you have to translate your plan into actual actions that you can take on the robot. So that's the common trait for robotic computing. It's more or less like a static data flow pattern, for one thing. Also, different robots would have different blocks here. Say for the cleaning robot, you may not have 3D perception, but you definitely have 2D perception, or the other way around. Some robots, cleaning robots, have 3D perception, but they don't have 2D perceptions. They don't have tracking, but they do have planning. So they are subsets of this diagram. So this diagram pretty much captures all the workloads that go into a autonomous robot. Now, we kind of understood the common trait or common workloads in the robot. How do we do it as a company and as a researcher myself? So that's our approach. We start with algorithm from different building blocks based on our different usage scenarios. So we kind of work on the algorithm to refine it, to adapt it to a specific workload. Then we publish in the venues in robotics, IROS, ICRA, RSS, IL, and so on, just so that the community understands what we are doing, and then we can form discussion groups so that we get some feedbacks for our product, for our progress as well. Then once that's done, we go into the prototype phase. A lot of work we talk about have gone through the prototype phase, such that we publish FPG, FCCM, FPT, and so on in the FPG conferences. Then once the prototype is done, if something is very good, we say maybe we can kind of modify the architecture, or we can define an architecture for this kind of workload. Then we try to publish in architecture conference, ASP, DAC, ASPROS, Micro, and so on. Then eventually we'll go into, for some of the prototypes, we go into the ASIC stage, VLSI, ISSCC, and so on. So I'm very happy that this year, 2021, we have 2 chips going to the ASIC prototype stage, that has gone through from the algorithm, FPGA prototype architecture, and then finally reaching the ASIC prototype stage. We have a chip on a computer vision processor for localization this year. So very happy to share that once that's out. So why? Again, that's how we do it. And we sort of talk about why we work on robotic processors, but we did not talk about why we work on autonomous driving computing systems specifically. So here's the stack. It's a very common stack for autonomous driving. And we just had discussion about the book. That's the book that discussed this stack. So there are different workloads over there: GPS, IMU, LiDAR, camera. Those are the sensor processing or the sensing workloads. What happens is that those sensors will grab information from the environment and try to convert that into semantic information that the computer can understand. So that's the job of the perception stage, including localization, object recognition, object tracking. Once you understood your environment, then you have to take action. So there's the decision stage, path planning, action prediction, obstacle avoidance, and so on. You have, any point in time, you have like 20, 30 tasks going on in parallel in the pipeline. So next thing, you need a very good operating system to manage this chaos. Otherwise, if, for example, object perception, object recognition takes too long, then it may crash the whole system, because the robot will just sit there waiting for an answer. Then there's no answer, then it doesn't know what to do. For a mobile robot that's moving slowly, that may be fine. But if you were talking about a vehicle that's traveling at 60, 70 miles per hour, that's disastrous. Then you need a hardware system to distribute the computation evenly, such that we can hit the deadline. And on top of that, what's more interesting is all these robots, if you come to think about it, it's actually, they are mobile systems. They need cloud support. Rarely we see papers talk about cloud, especially for robotic processing. But then in the cloud, a lot of things are going on. These vehicles, they actually capture data, environment data, to create a map so that it can navigate. So data collection and HD map generation is one task. Simulation, when you work on in a new environment, you want to simulate how your vehicle behave in those environments. Simulation is another very important workload. Then on top of it, you have the regular model training, then you have data storage and so on. So it's a very complex cloud as well. So that's first generation of computing system we use for autonomous driving. That was back in 2016. So we have a high-end CPU plus 8 to 16 GPUs, 60 TOPS of performance. Not a lot by today's standard, but back then it's crazy. 3,000 watts at peak. The cost is $30,000. And then you have to design special fans to do the heat dissipation. And on top of it, it doesn't do much. You just basic autonomous driving. That's where we started. So at that point, I was thinking, that may be the bottleneck of the whole autonomous driving workload, because if you have a complete system like that, it's not gonna go very far, especially in commercialization. If your computing system itself costs $30,000, how do you ship your product? So, so that's the basic motivation. So now we jump into more details how we got where we are. So there's a business story behind. So that's perception. We had a very short discussion. There's another book about the detailed technology we use. We try to eventually, hopefully, we can open source our technology. But we work on micromobility market. What's micromobility? Let's take a look. It's a very short video. So that's Japan, Hijiro Palace. That's a national treasure site in Japan. It's a very good tourist site. Then that's our small part or bus running around this national site to take tourists. It's like a 2 to 3 mile trip to take the tourists around. Especially in countries with aging population and very high cost of labor, this kind of solution is desperately needed. And that's our target market. So that's our product that you see from 2 years back, about 2018. But what's the story behind this product? So in 2016, 2017, we decided to do this product, but then we soon realized that we had a problem. The computing system, we don't have a very good computing system, but how do we move forward if we don't have a very good computing system? We got 3 options to move forward. Option 1, to optimize commercial mobile SoC, such as the Qualcomm chip, see if that can at least do basic autonomous driving workloads, such as low-speed autonomous driving. If that were successful, that we would be very successful because it's very cheap. You are talking about $200 chip that can handle the workload we just discussed, a very complex workload. And then second of all, they have a very mature software system already. And then it's backward compatible. So if they ship a next generation chip, you don't have to rewrite your software. On top of that, they have hit economies of scale, meaning that it's only going to be cheaper. So that's option 1. Option 2, let's buy some chips that people claim that can do autonomous driving. At the time, Mobileye, NXP, and some other companies, they offer specialized autonomous driving chips. But then very expensive, especially when NVIDIA first launched PX2. The price is about $30,000 US per piece. We could not afford it because we do micro mobility. We don't do full mobility. Anything over a few $1,000s may not make sense for us. So option 3 is to develop a proprietary autonomous driving computing system in-house. That's good because we have full control, but then it also means that we have to spend significant amount of our budget on the project. We may not be able to afford it. So the full business story is in this paper. It's in an HP Engineering Management Review. So if you are interested in the business story behind, you are welcome to check out that paper. But let's go through the process. So first of all, optimization of commercial processors, mobile processor. We did try. We had a Qualcomm Snapdragon 820. We did put the full autonomous driving workload on top of it. But then we saw a lot of problems. First of all, interestingly, mobile processors, they are optimized for one workload at a time. So if you play with a cell phone, there's only one foreground workload at a time. That you can switch between different apps, but one workload at a time. Second of all, so going back to the one workload at a time story, robotics, they are running like 20, 30 workloads at a time simultaneously. Any one of them becomes a bottleneck, then the whole system slows down. So it's a different logic in terms of design.
Can I ask a question here?
Sure, go ahead.
So I'm curious about that. Is that more because of the operating system and the software stack, or is there something fundamental to those chips? Because those chips are, they're what, 8-core, 4 big, 4 little, or whatever, right? Processors. So you would think they'd be able to handle more than one application at the same priority at the same time.
That's a very good question. We did, when we started trying that, we had the same thinking, right? You have, for example, Snapdragon, you have CPU, GPU, DSP, and the CPU is multi-core, very strong system. The problem is that the I/O bandwidth is not enough to sustain that kind of data copying, for one thing. Second thing, they don't have very good sensor support. So we're jamming a lot of sensor data into the chip simultaneously. It's the I/O that's bottleneck. It's the memory that's bottleneck. It's not you need to compute. So we summarize our finding in this paper. It's called Computer Architecture for Autonomous Driving. We kind of try a lot of things, but that's back in 2016, 2017. We try a lot of existing things and see that's what we have learned, the problem we have seen. We did successfully drive a robot at about 5 miles per hour using a Qualcomm chip that performs both localization, perception, and planning control. But then not for vehicles though. For mobile robot, maybe okay. So that's option one. It's gone. We spent about 6 months working on it, but it doesn't work. Second option, specialized autonomous driving system, XP Mobile NVIDIA. Several problems that we have seen. So we did not try this approach. We analyzed it, but we did not try. First of all, it's a black box. You have no idea what's going on inside. They give you a accelerator, but what's coming out of it, you have no understanding. You have no control. Second of all, extremely expensive. And then most of them focus on one workload, which is deep learning, a CNN, to be more specific. But as you can see from the beginning, we have 20, 30 workloads. We cannot just accelerate CNN. So no, we could not take this. So that left us with the third option, designing our own on-vehicle computing system. So let's go through the process, how we did it. It's a micro paper. So if you're interested, welcome to check it out. So design constraints, let's look at design constraints. I think the computer architecture community, they focus on mostly computing performance. But what we see is much more than that. If you look at the diagram on top of it, there's computing latency, there's a transmission latency, which is the CAN bus. The CAN bus is the communication backbone between the computer and the actual control. Then after that, there's a mechanical latency. Then if you want to hit the brake, it takes this much amount of time to stop the car. And then we are not showing the sensing latency here. So if you add on sensing and sensing, CAN bus latency, mechanical stop, computing is about what 30, 40% of it. So if we only optimize computing, we're optimizing 30% of the end-to-end latency. So there's different latency throughput requirements. We show a lot of details in the paper, but usually for autonomous driving companies, it's a 10 hertz frequency, meaning that you have sensor data coming in, but you have to guarantee that you can produce 10 control signals, at least 10 control signals per second, meaning that 100 milliseconds, that's your end-to-end latency, worst case. Energy thermal, right? We run on electric vehicles. So a computing and sensing, if the vehicle did not have any computing sensing, say it runs for 10 hours. By putting on computing and sensing, it drops that to 7 hours, 7.7 hours. So if you optimize that optimize your operation hours. That means more revenue for the business. And then on top of that, you need more cooling techniques if you are computing. It's so-called very hot. Then, of course, there are cost and safety concerns. Eventually, it's a business. Say it's a $1 per chip business. Then how do you make sure that you can still generate enough revenue? So that means you cannot spend too much money on your computing system. Also, how do you guarantee your safety if you don't use expensive system? Well, we try to do it in 2 ways. You have a proactive path, meaning that you use the expensive sensor, camera, LiDAR to detect people. And then you have a reactive path, so sonar, radar. So you have multiple layers of protection. That's the basic design constraints. So another constraint is LiDAR camera. When we started, we did not use LiDAR at all because LiDAR is kind of slow. It takes a lot of time to do localization using LiDAR, and it's very expensive, whereas vision-based techniques are quite fast for localization, and it's quite affordable. But of course, LiDAR wins in the quality of detection. If you're talking about 3D points in space, LiDAR is the best choice. So understanding all these constraints, then we design, say, hey, what's our software pipeline? We are not showing our actual software pipeline. We show, because a lot of it are confidential information, but we show what's out there that's similar to what we have. For example, we list all the algorithm here that's open source. You can welcome to try it out. It's very fun to play with ELAS, for example. Then we have the sensor synchronization problem, a huge amount of sensor data coming in at every second. Then you have to pre-process the sensor data, do some fusion and so on. Then go into two pipelines. One is localization, so that the vehicle knows exactly where it is at any point in time. The other part goes to scene understanding, or the deep learning pipeline, to understand what's in front of it, what kind of object can you detect. And those pipelines will produce localization result and perception result. Then we combine them into a collision avoidance system and path planning system to produce output. So we do exploit task level parallelism to try to parallelize sensing, perception, or this workload can be parallelized. For example, different sensor processing can be parallelized. You don't have to use the same processing unit for LiDAR processing and for camera processing. A lot of it can be parallelized. It's a matter of how you parallelize those to make sure that you have the most efficient system. So eventually we have a system like that. So we just jump into conclusion. You have to deal with sensors. Dealing with sensors is a pain. And then usually computer architects don't think about dealing with sensors, but it's a pain. Then remember we started with say, hey, can we use mobile computing platform? Can we use proprietary? We ended up using FPGA plus conventional CPU plus GPU architecture. Why FPGA, right? It's the exact question we asked at the beginning. FPGA has perfect I/O interface. You can control any sensor you want. It's I/O rich. You can send a control signal to trigger any kind of sensor you want. And then you can process a huge amount of data at the same time using FPGA. So FPGA is perfect for sensor processing and pre-processing. For a lot of camera data, you need to do pre-processing. Then by using the FPGA platform, you kind of drop down your amount of data by 100-fold or 1,000-fold. Then you send that to the GPU and CPU for further processing. Then that makes the whole pipeline highly efficient. So some data, I'm not going to go into too much detail, but it just shows that the FPGA design is very good at sensing processing. And then CPU is very good at planning. It's a sequential workload, iterative workload to be exact. Perception, GPU is perfect for perception. So you can kind of distribute workloads to different kind of processing units. And at the end, what's good about FPGA is they have partial reconfiguration. If you don't like one piece of algorithm, you can swap it out using FPGA hardware techniques. That's quite efficient. You can do it within 3 milliseconds. So I see a lot of FPGA firms selling their products, but they don't promote this great feature, partial reconfiguration. But I think this great feature, it's very beneficial for robotic workloads. Performance characterization, so that shows our variation in latency, and then the breakdown, how much time if you look at it, how much time sensing takes, how much time perception takes. So most of the proprietary or specialized computing system design focus on perception. So that's like 40% of the workload, but a lot of it go into sensing, some of it go into planning. And by the way, we're using a very lightweight planning pipeline. That's why it's barely 10%. But on the right side, you see, okay, if we delve into perception, what's the breakdown, right? For depth perception, detection, tracking, localization, you can dig out all these details from the paper, but it's quite interesting breakdown. A key point in this paper is the sensor synchronization. Sensor synchronization is seldom studied in academia, but extremely important in the industry. So you are dealing with so many sensors. Imagine you have a person has 2 eyes. If your left eye is out of sync from your right eye, then you don't see things clearly. Same for robot. You have different cameras, you have radar. How do you make sure that the camera detects the same object as the radar if they don't live in the same time axis? So sensor synchronization is an extremely important problem in industry. So we have to design a sensing and computing together. Meaning that we have to, for example, the figure on the right, at the bottom right, shows the image processing timeline. You hit the trigger, say, let's take a picture. Then it goes into exposure. Then once it's exposed, the picture will get transmitted. Then it goes into the ISP for signal processing. Then it goes into DRAM and CPU. Really depending on where you fetch the data. If you fetch that at the application layer of the CPU, then there's a huge variation here because you have to go through the driver, the runtime, the application. It could mean 100 millisecond variation. Then if you are experiencing 100 millisecond variation, there's no way for you to sync. But imagine if you do your timestamping in the driver, then you reduce it to, say, a few millisecond or maybe 10 millisecond variation. But if you could timestamp it at the sensor, that means pretty much no variation. So trick for sensing computing co-design is to have your FPGA to trigger the signal or timestamp the image at the sensor side, not at the main computing side. That will greatly reduce your variation, and then you get very clean information for further processing. And that's our sensing architecture. Basically, you get a signal from the GPS. Interestingly, the GPS not only gives you the location, it will give you a global clock, atomic clock called UTC. So that you get the clock signal, then you use FPGA to distribute the signal to different sensors so that everybody now lives in the same time axis. That's how we achieve sensor synchronization. So we kind of went through the long paper quite quickly, but some concluding remarks for this paper. We have to move beyond a lot of research in the past 5-10 years in autonomous system or in deep learning. They focus on optimizing one part of the computing system, but that they don't look at it from a bird's eye view. We need to understand the constraint and trade-off from a system on vehicle perspective, the whole system. So it's not just one accelerator you need to work on. You need to exploit the interaction between the accelerator across accelerators. And then the pattern, if we look at it from a very abstract view, it's a data flow pattern, but each stage, they impose additional constraints. That's robotic computing, right? The first constraint, you go in, then the image tells you you are around this area. That's your first constraint. Then you go through the second tracking stage. Oh, you are between this meter and that meter, say a 5 meter distance. That's your trace. Prediction says, oh, okay, then in the next second, you would go from here to there. So more and more constraints get added on the information. Then at the end, planning would add on this information and say, I have a constraint, I cannot go over 40 miles per hour. Then given all these previous constraints, what do I do next? So that's basically robotic computing. So more and more constraint, and then all the workloads run simultaneously instead of one workload at a time. So that's the basic traits for autonomous machines. So that's the first piece of work that we work on.
I have a quick question.
Go ahead.
So do you do any kind of real-time scheduling or something? Is there any work done on the scheduling side of all this? Because it might
Yes, a lot. If you're interested, check out the paper. We do have a lot of scheduling problem there. We did not dig deep enough, but it's huge realm of research opportunity over there. Because at the beginning, as we said, it's a 10 hertz output, but how do you meet that 10 hertz deadline, right?
Right. Okay, thanks.
So if we zoom out to look at this paper, what does it talk about? It talks about using existing compute substrates, meaning FPGA, GPU, CPU, to form a system that fits this kind of workload. So that's this whole paper is about. Then next, then we start thinking about problem. We zoom into another workload within this whole end-to-end computing system. Say localization is really common in all the different kinds of autonomous machines. Can we do an accelerator for that? And then can we bring that into an ASIC chip? So that's the second question we ask. So that's going to appear in HPCA 2021. So what happens is that when you look at localization, especially vision-based localization, there are pretty much only 3 things happening. The first thing, it's called visual inertial autonomy, or VIO. What means that you don't have a map, you don't know, you don't have a known environment to go with. You just get your localization as you go, as you travel, by using vision and inertial or IMU data. The second part is called SLAM. Say if you're indoor, you have good enough map, then you can, as you travel, you can also create a map. The reason that it's indoor, because indoor there's a size limit, outdoor there's no size limit. You can not create a map that covers, say, 10,000 miles and still have a smooth working system. So SLAM, it's pretty much an indoor technique. If you have a small room that you want to localize within, then you use SLAM. The third technique is called registration. Oh, that's meaning you already have a map. Now you have to track against the map against no map, using a map to help you to localize. So you don't have to create the map again. So that's indoor, but that's more efficient. So basically, we have these two axes to represent the scope. You have when you do not have a map, but you have a GPS, you can use VIO. When you have a map and you have a GPS, you can use VIO. But if you don't have GPS, you don't have a global signal, you can use SLAM. When you don't have a map, you can use registration when you have a map. As a mobile robot navigates indoor and outdoor, encountering different kind of environments, that's the taxonomy of localization you're dealing with. So here shows how it works. If you have two cameras, the camera will sample the environments, then we do feature extraction, then we do so-called temporal matching, so matching the frame from the previous frame. Then we have spatial matching, that meaning that matching your left eye signal to the right eye signal to create spatial information. That's our front end, right? Once you know what you see and you know the depth of objects that you see, so you understand the environment around you, and you understand what have you seen before. Then you compare what you are seeing now to what you have seen before, then you kind of know how much distance you have traveled. That's the basic logic. Then in the back end, it's filtering, fusion, and optimization to optimize your observation. So it's a front end and back end problem. But again, our design logic is, are there any common traits that we can extract from these workloads? Can we design systems that leverage these common traits to build a efficient system? So that's front end, and we do profiling on FPGA. In this case, FPGA is pretty much the precursor of our ASIC design. We try to verify the design on FPGA first. It's much faster than Intel CPU when we do front-end computing, 4x acceleration with 30x power consumption, less power consumption compared to Intel when we do this kind of workload in FPGA. Again, a lot of details. I'm not showing all the technical details. A lot of details are in the paper. You're interested to, you can check out the paper for more details. And then when we look at the front end, we compare two workloads, the car workload and the drone workload, because there are a lot of micro drones, indoor drones today that requires localization as well. The baseline, it's basically running program on ARM or Intel. Then we compare the FE here, meaning feature extraction, part of the front end, SM, stereo matching. So those are the front end workloads. So for both cases, whether it's car or drone, using front end acceleration, it's much better. So we, in the first part of this study, we kind of learned that front end processing, it's much more efficient on a accelerator because the characteristic of it, you kind of extract points from different part of the picture. You can divide the picture into different chunks. Then it's very hard for CPU to do this kind of workload. It's too heavy for GPU to do this kind of workload. So FPGA is a perfect fit. Then that's front end. And what about back end? What does back end do, right? Back end is basically doing optimization. If you look at the figure on the left, that pretty much illustrates what's happening in the back end. If you take a camera and take multiple pictures of the same object, although it's a mono camera without depth information, by combining all these pictures, you can recreate the scene through 3D reconstruction because you can now optimize all the reprojection from 2D space to 3D space and so on. That's how Google Maps works, by the way. If you go to Google Earth, Google Map, they have some 3D reconstruction that's using the exact same technique. And this technique is called bundle adjustment. It's also very commonly used in localization to optimize the trajectory of a robot. So that's backend computing. Same for backend computing. When we do it on FPGA, we leverage its the observation that they have different. Well, I will not go into details. It's quite complicated, but they have different projection points each time. Then you can design accelerators to optimize the logic for calculating this chunk of reprojection or that chunk of reprojection. But eventually, it shows much better results when we do a back-end acceleration. So the next thing is to combine the front. Oh, I only show here, but the next thing is to combine the front end and the back-end computing so that it forms a perfect system that into three forms. Registration, meaning that you don't have the back end because now you just have to compare against the maps. Basic compare and match operation. So using that, we are better than the baseline using FPGA. The second computing is VIO. You have a very small backend because you travel as you go. You just have to compare the previous 10 frames. Then still much better than the baseline. For SLAM, you have a very heavy backend. So the backend is 70% of the workload, whereas front end 30% workload. You are much better than the baseline. So we kind of define a system that's much more efficient compared to the CPU or GPU counterpart, because it's a piece of FPGA that you can decide whether you use the backend or not, whether you use the heavy backend or the light backend. It's very dynamic. That's how we achieve very good efficiency in this design. And this year we're gonna produce an ASIC chip based on this design. I'm sure it will be very useful for different kind of robots, because now you kind of look at the common traits of localization computing. You kind of divide it into, say, that's the front end, that's the back end, that's a common trait, and that's how you design the software. And when we design this system, we demonstrate that on FPGA, it's much more efficient compared to existing processors. The next step, we go to ASIC, see if we can bring another 10x improvement. So that has been our logic, and that has been our workflow. So that's pretty much it for this piece of work. So to summarize a little bit, we have front-end processing. We have designed the full system. We have designed a specific accelerators. Then you wonder, what are you guys doing now, right? And what are the conclusions you draw from those studies? So here are my personal take. You might not agree with me. That's fine. That's how we drive the field forward, because we disagree. So existing mobile SoC are not suitable for autonomous machines for the reasons that I have mentioned. It's not the I/O bottleneck, sensor design, and so on. But FPGA, meanwhile, for the next few years, I think it's quite suitable for robotic computing. It takes care of I/O beautifully. It gives you flexibility in the design, and we demonstrate that it's much better compared to Intel or NVIDIA counterpart. But that makes me thinking there may be 3 approaches in the future when we design robotic processors. Can we fine-tune existing architectures? Maybe we can fine-tune Intel architecture to make it better handle sensors, that we can have a very efficient design. We never gone down that path before. Can we do a software-only solution such that we can, if we can compress the network good enough, maybe software-only its approach? Can we develop different kind of ASIC and develop a robotic SoC to combine everything together to have a data flow-like architecture? We have tried some of them. I mean, fine-tuning, that's pretty much our micro paper. If we take it to the next step, that's fine-tuning and existing architecture. That's quite interesting. Second approach, we did a project called Cocoa Pie, meaning that we're using software-only pruning techniques for autonomous driving or any kind of deep learning workloads, and see how far we can go. And robotic SoC is basically our HPCA paper expanded to different kind of workloads. Say if it's one workload per module, then how do we combine these different modules together to form a very efficient SoC? So that's been the design logic. So we are pretty much out of time, but quickly I will go through a few more slides to show you guys what we are working on. We are working on infrastructure aided autonomous driving. The logic being that if you can share the sensors on the infrastructure side instead of installing all these expensive sensors on the vehicle, it may be more efficient way and safer way to do things. So I show a few small demo here. So here, when you drive, that's what you see. We do it in a simulator. And you go forward, there's a blind spot and someone jumps out, you may not be able to detect it, then you might crash. So that's what humans see. And that's what an autonomous vehicle sees. It's LiDAR, right? It uses LiDAR to see if it's the same scene, only the person jumps from the left side instead of the right side. The person jumps out, and that's what the robot sees. It's all these LiDAR points. Based on a few small points, it has to decide that there's a person jumping out. And if it's a blind spot, then you cannot detect it. Then here's the bird's eye view. If you have a small item here, you see a small light pole, although it's not a beautiful light pole. That's actually a detector. You can, we have LiDAR and camera on the pole to detect any objects around it, and then you can pass that signal to the vehicle. So as the vehicle goes forward, if a person jumps out, the light pole will give a warning, the vehicle will stop. So that just illustrates that what we are doing right now.
So can I make a comment on that?
Go ahead.
Yeah, so one of the things that strikes me is if you're a human driver and presented to that situation, right? If I'm driving 60 miles an hour in a busy city and, or I don't know, 45 miles an hour, let's be more realistic, or something. And I see that there is something blocking my view, I'm going to inherently become more cautious, right? So like, I know that I don't know, and that's why I'm more cautious. And I wonder if that's something to think about, basically trying to identify the situations in which it's not that you know that something is going to be in your way, as much as it is identifying the situations in which something, I don't know what might be in my way. Does that kind of make sense?
Yes, I think you are a very good driver. Statistics tells us that, let me give you the statistics to make my argument. So it's a study done by MIT, I think 2 years back. So human drivers in the United States, the crash rate per million miles, if you travel 1 million mile, human drivers is 4.2 crashes every 1 million mile. Most of them are fatal. So that's pretty bad. So autonomous driving, right? If you talk about Waymo and any other kind of vehicles, it's about 3. So 3 crashes per 1 million mile based on the data we have right now. So by providing a bird's eye view, a global perception of the environment, it provides 2 benefits. First of all, you don't have any more blind spots. Second of all, your sensor, if you think of it, your sensor, if you are a Waymo car, your sensor gives you a perception range of about 100 meters, effective perception range. But then if it's infrastructure aided, you can see as far as you want, as long as the road is equipped with those sensors. So you can make decisions much earlier. So that's why we think it has the potential to bring the crash rate to almost to 0 if everything is done right. So that's the argument. So basically I listed 3 stages of the development of this technique. The first stage is called infrastructure augmented, meaning that you have sensor on the car as usual, but then there's augmentation from the infrastructure side to give you additional information to make sure that you're safer. Stage 2.
There's a
Go ahead.
question, like someone like Elakin raised the hand. There's a question from audience. Elakin, you can go ahead.
Yeah. Can everybody hear me?
Yes.
Yep. Go ahead.
Awesome. So just to follow up on Dr. Grad's question, what I am also looking or intuitively trying to visualize is that if God's eye view is not present, for example, let's say that it is present, but there's a car blocking and then there's another car blocking your other view. So you have like a 2 sideway blind spot. And so that means that it still can be avoided because then you still have a potential of a crash. In that situation, how would an autonomous vehicle respond? And to better put it is, what other action does the autonomous vehicle would take? Because if it was from a human perspective, if there is unexpected person just jumps into your view, then we would probably swirl to either the right or the left in order to avoid a disaster. So it's easier to like hit one of the vehicles or just swirl to an empty spot. Would the autonomous vehicle also take that sort of reflective response?
Well, that's a very good question. I think really the answer depending on the planning strategy of the autonomous vehicle. But what I'm saying is that with infrastructure aided design, you can have a lot more information to process. We are still going through the same pipeline, but you have a lot more information available to you. Then you, based on those information, you can design new planning algorithms to deal with different kind of situations. So I have to emphasize that this field is just at the very, very beginning of it. I think we are one of the first companies in the world that's dealing with these kind of problems today, that we have full set of sensor on the roadside. We understand the scenario, we understand the new challenges, but still, we are still at a very early stage. We don't have answers to everything. But if you look at the design, that I'm just going to discuss. If you look at design, and then on the next page, I'm going to show you more technical details of the design. Then probably that design will answer some of your questions, how we're going to deal with these kind of problems. So in the design, the first stage is to ensure safety by still using your onboard, on-vehicle planning infrastructure. So how you tune your planning algorithm really depends on the autonomous driving company, but we are making more information available to you. You have the full set of sensor available to you. You have to fuse the sensing information from your own vehicle with those from the roadside to make a safety decision. Second stage, what if you say, hey, it still doesn't make sense to me. I mean, I'm spending that much money on the car, and then I'm spending additional money to the infrastructure. Economically, it doesn't make sense to me. Then the second stage will be infrastructure guided autonomous driving, meaning that all the proactive perception will be offloaded to the infrastructure. So no more expensive LiDAR on the vehicle, only passive or reactive sensors such as radar, sonar. So going back to your question, if someone jumps out, the car is equipped with reactive sensors. Worst case, it can just stop. It can just brake. But then with the infrastructure, if the infrastructure is designed good enough, it can cover long distance and all the blind spots, then you don't have to brake very hard. So that's a cost issue, right? Because now you are pretty much offloading the most expensive part from your vehicle, meaning the sensing and computing, to the roadside, to the infrastructure side. Then all the vehicles are sharing the same infrastructure. So that's the second stage. The third stage is that in the second stage, you still have to do planning. You have to plan your own action in the car. That will still take up some computing power, and it's still an individual decision. Each car decides how it wants to plan its action, but you just have more information available to you, but you still have to plan your action in the stage 2. But in the final stage, infrastructure planned autonomous driving, you have a global planner to take care of the planning for each vehicle, such that you can really achieve maximum traffic efficiency. We have done our own simulation in-house. We developed a very good traffic simulator, bringing in real traffic data. By hitting this stage, it's very easy to improve traffic efficiency by 40-50%. Easy. I mean, using just basic algorithm, you can improve it by 40-50%, because now you have more information available to you. You have you can do a central planning for any kind of traffic situation. So that's the stage we envision. But what does that mean, right? Eventually, this is the technical talk. What does that mean? And then we have talked about all the pipeline before. So here's what it means. The same pipeline I showed you guys at the beginning, sensing goes into perception, localization, tracking, prediction, and so on. So we added 2 components to the vehicle. One's the OB onboard unit that receives signals from the roadside. The SOR, meaning that system on road, so infrastructure that will produce data. So when infrastructure produce data and send it to the OBU would see which module should I dispatch the data to. If in this first stage IAD, then the module will say, hey, let's send it to tracking. But then the vehicle itself still takes in its own perception data, but it takes additional perception data from the roadside. Then they combine data into tracking so that you are not saving anything because you still have to do the heavy lifting over there. And then you have more information coming into you. So it puts more stress onto the computing system. And more interesting to it, it's that you have a deadline to hit. Somebody just raised a question, we got real-time computing. Yeah, that's the perfect case of real-time computing because someone is sending you data through the network. Then what if you miss that deadline? Now, for one frame, you don't have infrastructure data. How do you deal with reliability? Just relying on onboard data, right? So there's a whole realm of research areas. Tons of research has to go in before we can ship reliable products in this field. Then in the second stage, IGAD, then you say, hey, the OBU will dispatch data to planning because now I don't need any local prediction, tracking, perception, everything is done on the roadside. I just have to do reactive perception for safety's sake. Then, yeah, you get rid of all these heavy lifted computing, but then real time is a huge issue. Security is a huge issue. Reliability is an even bigger issue here. Then at the end, if the central system controls the car, then it becomes a privacy and trust issue. So a lot of problem we are dealing with. So, but that's what we're working on. But very last slide, what does it look like, right? Will you ever wonder what does it look like from the roadside? And here's a very rough picture. We cannot disclose too much information since the project is still confidential, but that's how it looks like using LiDAR to track moving traffic from a so-called bird's eye view. I don't want you to use God's eye view. I don't want to offend anyone, but it's bird's eye view. So that's how it looked like real-time traffic. So yeah, that's the end. A very fun talk and very nice talking to you. Really looking forward to collaborating with you. I think collaboration really pushed the field forward.
Excellent. Well, thank you so much for that.
Thank you.
No
There's
problem.
a question from like a student like Fei Wen. Can you go ahead?
Hi, Dr. Liu. Thank you for the great talk. I find it very interesting because my own research is also focused on FPGA and embedded system. So I have a question regarding the collaborative driving. So the current solution you just mentioned is to say set a LiDAR on some in the surrounding environment and provide like a bird's eye view. But is it possible to collect those information, say, from the second party, like pedestrian in this scenario? So because nowadays everybody is carrying a cell phone, right? Is it possible for the pedestrian to kind of send out some information or signal from their own cell phone to notify the surrounding cars that, okay, I'm walking around this area, so just watch out for me.
Well, very good question. I have to write another business case study just like the one I wrote before. We did try that. We did try
and
that.
It doesn't work?
Yeah, it really doesn't work because you don't get the full view of the environment. You're really depending on a few guys contributing. It's called crowdsourcing approach. We did spend a year doing research, collaborating with different universities on that. Doesn't work because you don't have a global view. Then you're never going to reach the centrally planned or centrally guided approach that would reduce the amount of sensor, because you cannot trust. Say it's blind spot, someone carrying a cell phone, but what if that cell phone is not sending you any signal? What if you miss anything? There's no guarantee. And what if you are at a very crowded street, but people try to inject forceful information into the system? So there are a lot of problems that we have to deal with. But that approach does not give you enough information so that you can understand the environment. And then it's very hard to fuse those kind of information.
Okay. Second question is about, because in the very beginning you said the bottleneck, like when you try the first approach to optimize the off-shelf mobile processors, you said the bottleneck is about this I/O bandwidth and latency. Later on, when I show your architecture, I noticed that you use the PCIe, right? But we all know PCIe, because from my own experience, PCIe has a very high latency. Have you ever considered like using creating your own bus protocol that support high bandwidth and low latency? I know like IBM, they have their CAPI, maybe some other companies working on something themselves. So why do you chose to use this FPGA plus like a commodity computing platform rather than designing your own SoC or bandwidth from the beginning?
Another good question. We are a company. So a very short answer, we are a company. So we deal with the most realistic solution.
Okay.
The paper itself is trying to inspire the community to try different approaches, see what's the best approach that we have right now. We are just trying to share our experience, try to inspire the whole community. But after all, we are a company. We're not Intel Research. First of all, we are not Texas A&M. We don't have that kind of resources to try every single approach. But that leaves a huge opportunity for further research into this field. After all, it's the very beginning. I mean, our paper, the micro paper, is pretty much the first few papers in this talk on this topic. But robotic computing, I'm a big believer in that, because we have gone through an Intel era. the PC era, pretty much powered by Intel. Then we have gone through the mobile era, pretty much Qualcomm and all these ARM processors. And if you ask me what's the next big thing, I would definitely say it's robotic computing. But then we are a very small team. We don't have that kind of resource to explore every single option.
Okay. So how open are you to like external collaborations, or is it most of the paper just written within?
No, we're super open. That's why I'm even here, right? I'm even here. I mean, interestingly, one of the review we got for our paper submissions, why are you guys disclosing your information? But then, like I said, it's the very beginning of the field. Through the academic collaboration, we actually learned a lot. For a lot of scenarios we did not even think about, but because of our academic or research collaborators that make us to think in the right direction, that really help our engineering. So our culture is quite open to different kind of collaboration as long as we can push the whole field forward.
So we have a few other people and we're almost out of time. So let's go ahead and take some other questions from other folks. Let's see, Dao Jing, do you want to go next?
Yes. Hi. So when you speak of the that 3 stages, and actually, I'm very interested in because I'm also so my research side is about like providing the real-time like remote information update, like to ensure each information flow got enough data, and so basically in my big picture, I have think about all those 3 stages you have mentioned, and do you think about that? So when you're talking about like, even though we are accepting some decision or some information out of from the infrastructure side, and you mentioned that there may be some, like for example, the real-time information problem here. Maybe the information will be lost, or maybe it will be out of a deadline. So have you think about so how do I say? So will you think about that? So even in the car side, even where I'm doing the passive, like receiving the information, but I also do some estimation, like based on all the information I received, I still will do some estimation to help my action next.
Definitely, but my short answer is we're not there yet. We're still exploring a very early stage. Every step that we push forward, we open up a bigger door to a much bigger research problem, a lot more research problems that would pop up. And then each time I give a presentation like this, then we receive a lot more good questions regarding, hey, can you do this? Can you do that? But I think, again, we are constrained by, limited by our resources. So hopefully the academic research community can pick up. I'm here to inspire you. It's a very interesting topic with great potential. Maybe it defines the next 10 years of computing, especially when we started, it's only on board or on vehicle computing with single machine. Now we're dealing with, say, 10,000 machines fusing all the information together. What kind of information is useful? How do you meet the deadline? How to design system? A lot more problems will pop up, including yours.
Okay, yeah. And the second question, maybe a small question, is like, so I'm wondering what is the difference, like the main difference between these 3 stages you mentioned and the what we call the V2X, the vehicle to everything, or maybe the collected and autonomous vehicle, like network.
Yeah, the terms out there are so confusing. The terms out there, they abuse the V2X term. V2X is only for communication, to be exact. So V to X, whatever X is, right? It's how do you send information from V to X or X to V. That's all. That's the backbone. It's like asking, oh, well, you are doing computing, but how is that related to your computer network? So I think it's the same kind of question, but I think the term has been abused.
Yeah, thank you. Yeah.
So let's take one more question, and just to be respectful of Professor Liu's or Dr. Liu's time, let's see, Srini Dihi. I don't know if I'm pronouncing that right.
Yes, thank you. It's the same question as before. I was wondering if we can use GPS to let the car know that there's a pedestrian walking, and will it be possible to interface GPS with the maps to let both of them know, like let the pedestrian know, like the car is approaching in the road, and as well as the car know the pedestrian is walking.
So if I get your question correctly, you mentioned, can we use GPU to pick up
GPS, the tracking.
GPS? Yeah, of course. I mean, in the perfect world, if everybody's carrying a device, that device is sending signal, then of course, yes, but the world is not perfect. We cannot trust one source of information. It's too easy for hackers to inject false information. And on top of that, if someone is not carrying that, then you pretty much miss that. So I think it's very hard. And then even on top of that, are you willing to share? Right. It's a privacy concern. It's a policy thing. It's out of our realm.
Okay. Thank you.
No problem.
Okay, so we're a bit over, so I think we're going to have to call it there. I know there were some more questions, but it was but I want to be respectful of everyone's time. Thank you so much. What a wonderful talk. Imagine a thunderous virtual applause at the end of your talk, with everybody unfortunately with their mics muted.
A real pleasure seeing you again. We met just before the pandemic with one show, but it's great to see how much you have done since. So it's great.
Well, thank you so much. Likewise, I mean, we are quite open for collaboration. I think it's a huge opportunity for research, a huge field. So if you're interested in this kind of work, send me an email, then probably we can establish some collaboration and to solve some of the problems that you just brought up. But again, I'm very excited to have the opportunity to work on this field. And